Hi, my name is Gunnar Prieß and I'm Research Associate at the German Aerospace Center and the Hamburg University of Technology. This year my speech will about networking of fuel cell stacks using Wolfram System Modeler and Mathematica. Thanks everybody for joining. My name is Gunnar and I'm a Research Associate at the German Aerospace Center at the Institute of Engineering Thermodynamics, and I basically work on electrochemical energy technology. And today I would like to talk a little bit about very recent ideas concerning the networking of fuel cell stacks, which means that in the typical fuel cell systems you have only one type of fuel cell stacks, and compared to battery modules or arrays of capacitors, we were considering of using more than one stack into a single fuel cell system. And the first ideas I investigated very roughly using Wolfram's modeling and simulation suite. That means the software of Mathematica and System Modeler. The talk will be outlined. I give a brief introduction about the background of the systems, which we are considering, and what kind of applications, and I hopefully can also motivate the use of considering to have more than one fuel cell stack into a single system. And then we have a short look at one can get rid of single stack fuel cell systems using System Modeler and Mathematica very roughly, and how it is also possible with a few lines of code to make a decision whether it's a good idea to use more than one stack in a system. And I will summarize and give a brief outlook, as Jan yesterday motivated me to show some video stuff which shows our very recent work quite well. So the background is that we are working on a certain kind of fuel cell system which is called multifunctional system integration. That means we use a fuel cell system not only for providing electric energy for different purposes, we also use it for providing thermal energy, as well as inert gas and product water, which are made from the products, the process side products from the electrochemical reaction. And that means that compared to a typical fuel cell as electrochemical energy conversion or a combined heat and power plant, we have several observable products we would like to control independently, and each of these products which need to be controlled to a certain demand, to a certain load profile, has impact on the other products as well as on the operating of the fuel cell itself. So that is a kind of tricky optimization problem with lots of trial and error, and that's what we are basically doing. And I don't know whether it's readable, but this is an example of a fuel cell, multifunctional fuel cell system for future generations of civil aircraft, where he has written typical purposes for the product that we use the thermal energy for ice and rain protection, warm water heating, also for the air conditioning. Electric energy obviously is used for electric power supply, also autonomous taxiing when there is an electric engine in one of the wheels of the aircraft, air conditioning, electric heating. We use the product water of the fuel cell for potable water, processed water, also for humidification in the air conditioning. And the inert gas is used for, if it's dried inert gas, we can use it continuously for fuel tank inerting. And if it stays wet, we can use it, we can store it somehow and use it eventually for cargo fire protection. Yeah, and to show that it's not only research, we also have some kind of applications. This is our kind of largest laboratory. It's an Airbus A320, and I think it's not readable, but it's a large sticker here on site, fuel cell demonstrator, and the fuel cell system is located here. It's at the moment not replacing the conventional gas turbine powered auxiliary power unit. It's just, so to say, a spare part for testing, so that in case of emergency we can go back to the conventional systems. Here maybe some of the people from Germany and Europe have once driven with the Scandlines ferry, which is also completely powered by hydrogen-based fuel cell, which is connected also to the heating system and the onboard power electronics. This ship is quite impressive since there are also some more advanced techniques like these flattener rotors for harvesting wind energy for propulsion. Here we have one of our buses from Hamburg Public Transport. This is a high voltage DC battery powered bus which has a fuel cell range extender, and the most tricky stuff is here. It had on the roof mounted fast charging device, so that there are certain bus stops on its route where there are few minutes standing time, so this bus can always have an induction rapid charging mechanism to recharge the battery during the stop. And if it's not enough, then the fuel cell will come up as a range extender. This product is already commercially available. This is a phosphoric acid powered fuel cell system which can be used by the industry for providing electric energy, heating energy, also cooling energy by absorption cooling, since this operating temperature is roughly about 180 degrees Celsius. And the inert gas is used for inerting large rooms and also fire protection of special locations where it's needed. So all of these applications use fuel cell systems with a single fuel cell each. These commercially available systems can be sized. If you buy 2 or 3, that would be no problem. Then you have actually 2 or 3 fuel cells itself, but from the operating point of view, they will act as or behave like a single fuel cell in the control process. So what's the motivation for considering more than one fuel cell into a single system? The first advantage might be that the availability and the cost. The commercial fuel cells available are available in different sizes, and if you have a specific demand of power output, then it might be cheaper, and the fuel cells are really available if you can size your system with existing fuel cells and not have the need to design a special one adapted to your requirements. That might save time and cost. The reliability would be a point of view when you have several fuel cells and one causes damage. It might be that not the whole system breaks down because there are spare parts that can take over at least part of the load. Maintenance would be one point, because especially for the stationary applications, when there is a continuously running operation, people often ask whether it might be possible, if we have 2 fuel cell stacks, that we can have the maintenance procedure on one stack and the other one can go on with a partial load. And the question also would be, are there some possibilities to improve performance by having more than one stack? And basically, all of these points might be potential disadvantages if it goes wrong. So that is actually a point to consider. So, and let me briefly mention some points of basic single cell fuel cell modeling. All starts with the kind of polarization curve, which has inside the characteristics of all electrochemical energy technology. I here placed a very simple one, which is basically only shows the cell potential normed for 1 square centimeter, dependent of the current density. And here, actually the parameter temperature is in here, but I avoided all other parameters like pressure and mixtures of the gases and stuff like this. And such equations are very easy to set up if you know a little bit about the fuel cell. They are can be found in books. And but to fit actually the parameters that are characteristic for each type of fuel cell is not that easy, but in the first step, Mathematica always has some good built-in functions like find fit or even find formula, which can be used if you have experimental data, which are the points here. I collected some specific data from 4 different experiments, and then you can fit a polarization curve. Down here, I think it's not that well readable. Here are the parameters. The first fuel and oxidant, actually I choose because of the type of fuel cell, and then the reference potential is quite clear because of the reaction between hydrogen and oxygen, and you can see that many of these parameters can be directly found by Mathematica by fitting, or also included already in Mathematica, like the gas constant or Faraday's constant, which is quite nice because it also is able to provide a kind of dimension checking for you. Because if maybe someone has already looked up kind of polarization curve for an electrochemical energy converter in some textbook, sometimes there occur type of equations within the argument of logarithmic or exponential functions which make no sense since the dimension do not count out for each other. So it's sometimes hard to see how the people get there, and it's more a phenomenological fitting than kind of physical fitting at the end. From the polarization curve, it can be seen. Oh, that is very bad to read. I'm sorry for that. From the polarization curve, you can see actually that the behavior of such a fuel cell, the electrical behavior, needs to be nonlinear. So that is the best place to start using system modeler to show up how actually the response of this nonlinear behavior is. And it's actually quite easy if you start with a polarization curve to set up a model for a single fuel cell. You can either use the text mode and just putting in equations, set parameters, which you can take from textbooks or the literature, or you can even directly draw an equivalent circuit because all of these components are really available within the Modelica standard library, and so in system modeler. And let's see, then we can model the transient response, for example, of the cell potential if we have a current ramp, and there you see definitely that nonlinear behavior. And actually, if you know polarization curve with the fitted characteristic parameters, and you know a little bit about these transient response of the fuel cell potential, you know enough about a fuel cell to make the first investigations and the first thought of how to analyze, optimize, and improve this stuff. So basically, everybody can start afterwards trying to build at least the electrical side of a fuel cell. And the analyzing, that's really bad to see. The analyzing can be already done quite simple using just the simulation center of system modeler, like Jan and Patrick yesterday mentioned in their education course, just playing around a little bit and looking up what the different behaviors are and try to understand them and interpret them. For example, you see here, maybe you see, or hopefully you see, this is the characteristic polarization curve, which shows the cell potential in volt over the current density in ampere per square centimeter. This is the fitted curve from before. And if you simply draw this curve, which shows the power density, so the watt per square centimeter over the current density. This is quite typical for any kind of fuel cell. And then basically most people also draw the efficiency curve over current density, which is basically kind of replaced characterization curve, because there is a constant relation. And this shows the motivation via fuel cells considered to be quite efficient for low load, because for very low current density they show a very high direct electrochemical conversion efficiency up to the theoretical value of up to 83%. But what is more interesting, if you, for example, have a look at the efficiency curve over power density, so which shows you the electrical conversion efficiency over the power density. And that shows that it's really not that good conversion efficiency for very low loads. And actually, this was the point for starting to consider more than one fuel cell systems, because in practical applications at this point, you size down a little bit the fuel cell concerned to your actual load and hybridize it with a battery or something like this, so that you do not need the fuel cell to be operated in low efficiency ranges. You go here, and if your actual load demand is not that high, you simply charge the battery. And quite interesting is this, I have validated most of these models with an 80 kilowatt single stack fuel cell system in the laboratory of a certain kind from a Canadian manufacturer, Hydrogenics. And then I built up a reference test bench, which has also fuel cells of the same type, 80 kilowatt in complete, but it consists of two 10 kilowatt and two 30 kilowatt stacks. And if we now compare the different curves of efficiency over output power, then you see that this curve is actually the efficiency over power curve from the large single stack fuel cell system. So we see, for example, it has the highest efficiency of roughly above 50%, nearly shortly before the maximum power output of 76 or something like kilowatt. And here you see that a 10 kilowatt system actually comes up to the highest efficiency shortly before 10 kilowatt. So you see that the single system will not be operated in these regions. For example, for output power of 10 kilowatt, you will have here roughly about 10% of conversion efficiency, and here you will nearly have 46 or 47%. And so this immediately showed the idea of that we should try to use it, and the idea was to combine these 4 fuel cells in a way that when you draw power out of the system, that at the beginning only one of the system is loaded up to a certain amount, and then some passive components like diodes or stuff like this were taking one of the others into account, so that we get a curve which follows roughly such a shape. And it's easy to see that especially in very low areas of load, we get a very high efficiency. And unfortunately, I'm not able to show the algorithm which provides you the optimized configuration of diodes, but I can show you later on how we actually used it. So because of time, I will just briefly mention that we saw this dynamic transient response of one of the fuel cells, and it's not that good to see, but it's actually here that we have, with the black line, the power output of the complete multi-stack fuel cell system. And all of these curves are the power output of single ones. And it can be shown that the transient responses of each of these single stacks can be a little bit balanced in the complete output of the complete system if we have a very short temporal displacement between when we put the dynamic load on each of these stacks. And these both two things were quite easy to investigate using system modeler and a bit of Mathematica. And actually, I would have shown some bit more, but the first results were so good that I had to stop modeling, and we were starting to directly building a system which looks like this. I'm not sure whether there is sound. But the idea was to take an aircraft, two sailing aircrafts, and building a third wing in the middle, and placing one of these so-called fuel cell networks, as I call it, these multi-stack fuel cell systems in there, because of these passive components, it would also be possible to have a passive charging and discharging of batteries to create a kind of direct hybrid system, and this makes this system efficient and light enough to be able to power such an aircraft. We use here 4 smaller fuel cells. Each of them have roughly about a little bit more than 11 kilowatt of power output, both with 2 hydrogen tanks and 2 batteries, as it's shown here. Lithium polymer type, and also quite impressive current of up to 600 amperes. And this 4 passenger seated aircraft was intended to go up to 1,500 kilometers, and it should be kind of technology demonstrator for short distance, short distance connection aircrafts between smaller airports and larger airports, or different kind of airports in the near future. And since I should not only show that we intended to build this, I can also show, since nearly 2 weeks, that we actually finished to do this. So there was unfortunately a little bit less time to do more modeling and simulation, but due to some due dates and some kind of economic purposes, this project needed to be finished first. And this aircraft has a very general kind of fuel cell network installed, and it's intended to serve for the next 5 years as a kind of platform. I will go on with a more detailed systematic modeling based investigation of this fuel cell networks, and it's intended that kind of potentially topologies, configuration, and operating strategies can be implemented here and tested. And one of our test pilots was quite happy because actually this aircraft makes no noise except the aerodynamic noises of the fan. There is completely no noise. And we were able to improve, or to increase a little bit the storage pressure of the hydrogen, so it is now able to go up to 2,200 kilometers a distance without filling up. And basically, if you can increase the pressure of the hydrogen, it's more or less no more weight, since a few kilograms of hydrogen does not take into account very much. Roughly about 250 kilometers per hour. So yeah. There should have been music, but I don't know whether it doesn't work. So due to the lack of time, I think I will go directly to questions, if there are any. Thanks a lot, yeah.